Okay, in this video, we're going to talk about section 1.3 dealing with inverse, exponential, and logarithmic functions. All right, now I realize that the print is a little bit small in this video, but I will just pretty much highlight just the important information about what's being discussed here. But we will talk about things like exponential functions. We'll look at some of the properties of exponential functions. We'll also talk about one-to-one functions. And we'll look at finding the inverse of a function. And also we'll graph inverse functions along with the function themselves. And then we'll talk about logarithmic functions. Okay. And also we'll talk about change of base property. So again, this is just a review of some of the concepts that were in college algebra. All right, so we'll talk about exponential functions. They have this form, f of x equaling to b to the x. F of x equals to b to the x. And of course, b is a positive constant other than 1. That means b is greater than 0, but b cannot be equal to 1. Okay. And an important question that arises immediately: for what values of x can be b to the x be evaluated? Well, in this case, your x can be any real number. Okay, it can be any real number. But the restrictions on b, which is your base, is that it must be a positive constant other than 1. Okay. Now, there are some rules for exponents here. Okay. And I'll rewrite these off to the side since it's not clear on this handout. Okay. The first rule is this: if we multiply powers of the same base as b to the x times b to the y, that would be just bring over the base and then add your exponents, b to the x plus y. Okay. And this is for b being a positive number. And you have x and y being real numbers. And then E2 says if you divide powers of the same base as b to the x divided by b to the y, that means we bring over the base and then subtract the exponents. Okay. And this also does include 1 over b to the y, which is equivalent to b to the negative y. Okay. So we can include 1 over b to the y. And as a negative exponent, we write that as b to the y. And then the third rule is if we raise a power to a power, that's b to the x raised to the power of y, we bring over the base and then just multiply the exponents, that's b to the x times y. And the fourth rule, b to the x is greater than 0 for all x. And that makes sense because b is a positive constant other than 1. X can be any real number, so it's going to be greater than 0. Okay. Now let's look at some properties of exponential functions, by the way, which is f of x equal to b to the power of x. Here, b to the x is defined for all real numbers. That means its domain is going to be from negative infinity to infinity. And this is how it is written in interval notation. And b to the x is greater than 0 for all values of x. That would mean that the range is only going to be from 0 to infinity, because b to the power of x is positive. Okay. Number 2, for all b not equal, well, greater than 0 and not equal, and b to the 0 is equal to 1, that would mean f of 0 is equal to 1. Okay. So b is a positive constant other than 1 raised to the 0 power. That's going to automatically be equal to 1. which would mean for this function, f of 0, if you substitute, would be 1. Okay, and that will always be the case. Number 3, if b is greater than 1, then f is an increasing function on x. So like in this case, if b is equal to 2, then 2 to the x is greater than 2 to the y, whenever x is greater than y. Okay. And if b is between 0 and 1, then f will be a decreasing function on x. And that's, for example, if b is, let's say, 1/2, then f of x will be 1/2 raised to the x. Because if you simplify that, 1 to the power of x is always going to be 1. 2 to the power of x is 2 to the x. So you're going to have 1 over 2 to the x. But if you write that as a negative exponent, it would be 2 to the negative x power. Okay. So on the next page of this handout, you'll see what the graph of y equal b to the x looks like in these 4 different forms here. So as you let b get larger, you're going to produce greater rates of increase in b to the x, okay? Because here's y equals 2 to the x, and you can see for y equal 3 to the x is producing a greater rate than y equals 2 to the x, and then we increase the base to a 5, is going upward quicker, and for y equal 10 to the x is going up quicker than y to equal 5 to the x. Now, if we let our b be smaller, then what's going to happen here is you're going to have greater rates of decrease. So like y equal 0.9 raised to the x. Notice that this is almost a straight line. But for y equals 0.5 raised to the x, notice that you have a rate of decrease that's increasing, or well, a greater rate of decrease. And then for 0.1 raised to the x, there's a greater rate of decrease. But notice in all of these cases, the y-intercept is 0, 1. And that's always going to be the case. And the same thing here. The y-intercept is 0, 1. Because if you let x equal 0, whatever b is, with the exception of 0, raised to the 0 power is going to be 1. Okay, now on to the natural exponential function. Okay. This has the natural base e. Okay. So here we're using a special base e. Okay, now in this case, e is an irrational number. Okay, that means an irrational number is a non-terminating, non-repeating decimal. So anytime you have that, that's going to be natural base e, and e is going to be this decimal approximation. Goes on indefinitely without n, and there's no pattern of repeating numbers. So the natural exponential function will be f of x equal to e to the x. Okay. Now, what you're going to see here is the graph of what y equal e to the x looks like. And notice here that that graph crosses the x-axis, crosses the y-axis at 1. So my y-intercept is, again, 0, 1. Okay. As you can see here, for y equal 2 to the x, that's what that graph looks like. And y equal 3 to the x, it looks like this. Okay, and e to the x, where e is approximately 2.718, is in between those two. Now for the graph on the right, you'll see a line that looks like this. where it's touching the graph of y equal e to the x at this point, 0, 1. We call that the tangent line. We call that the tangent line. Okay. All right, now we'll look at inverse functions. If we want to consider the linear function f of x equals to 2x, okay, which can take any value of x and then double it. So here's a function that reverses this process by taking any value of f of x equal to 2x and mapping it back to x. We call that the inverse function of f. And this is the notation for the inverse of f with a -1 symbol. That means f inverse of x. So in this case, the inverse of function of this would be f inverse of x will be x over 2. Okay. So here's the formal definition of an inverse function. So if you're given the function f, its inverse, if it exists, is a function called f inverse, such that whenever y equal f of x, then f inverse of y will be equal to x. And it's illustrated in this figure right here. So going from from x to y equal f of x, that's your f, your function, where of course x is in the domain of f, and x equal f inverse of y will be in the range. Okay, but here if we go from y equal f of x to back to x, then it will be f inverse, where y will be in the domain of f inverse and y equal f of x is in the range of f. Okay. Now, if we have an inverse function, we will also have something called a one-to-one function. A one-to-one function. And here's the definition of a one-to-one function. A function f is one-to-one on the domain D if each value of f of x corresponds to exactly one value of x in the domain. Well, precisely, f is one-to-one on D if f of x1 does not equal f of x2 whenever x1 does not equal to x2 for x1 and x2 in D. Or more explicitly, you cannot have two different y values going to the same x value. Or I take that back. You can't have a y value going to two different x values here. No one y value can go to two different x values. If that happens, then that means you will not have a one-to-one function. Now, the horizontal line test is what we can use to determine whether we have an inverse function from a graph that's given to us. And the horizontal line test says that for every horizontal line, it's going to intersect the graph of a one-to-one function at most once. Okay. For it to be one-to-one, when you're using a horizontal line test, that horizontal line can only cross the graph at only one point. A couple of examples here are these graphs here. The one on the left has a one-to-one function. Here's the graph, and this is the horizontal line. You can see it's crossing that graph at only 1 point. So that is considered to be one-to-one. On the other hand, the graph on the right is not one-to-one, because if you draw the horizontal line, you're going to see it's crossing this graph at two different places. That means I have a y value with two different x values. Okay. The same y value with two different x values. So that's why it is not one-to-one. And this would also not have an inverse function. So let's look at example 1 here. Here we're going to use analytical and/or graphical methods to determine the intervals on which the following function has an inverse. And we're going to make each interval as large as possible. So in this one, we got f of x is equal to 2x plus 2. All right, what I'm going to do here is use the graphing calculator to graph this function. So I'm going to go to y equal 2, and I got stuck in y1, so I'm going to clear that equation out, and I'm going to enter 2x plus 2. So in this case, I'm going to type in 2 in y1, press the xt theta in for the x, plus 2. Then I'm going to do zoom 6 for the standard window. And you can see it's just going to be a plain straight line. Now, as we can see here, if we were to draw a horizontal line through this graph, that horizontal line will only cross the graph at one place. Only one place. So that means we do have an inverse function. Or we can say that we do have a one-to-one function, to be exact. So we can say that we do have a one-to-one function. And of course, let's say we want to make the interval as large as possible. Well, any x value that you assign to it, you're always going to get an f of x value for it. And the same holds true for the inverse. So that means from negative infinity to infinity would be the domain for this. Okay. All right, on the next page is another example. This time we got the absolute value of an absolute value function. So here f of x is equal to the absolute value of 9x minus 5. And here I want to use analytical and/or graphical methods to determine the intervals on which the following function does have an inverse. All right, so let's enter this in the calculator. So I'm going to press y equal to and clear this equation out. Now, this is absolute value. For me to do the absolute value, I will have to press the math key right here on the far left-hand side, the math key. I'm going to use my right arrow key to go to highlight the menu item that says NUM. That's the number menu. And look at number 1, ABS. That means absolute value. So I'm going to go ahead and select that by pressing number 1 or pressing enter. And it's going to give me 2 absolute value bars. Now, if you're using a TI-83, it's going to give you ABS with a left parentheses. But with the newer calculators, it'll give you the absolute value bars. And inside, you'll enter that expression, 9x minus 5. So 9xt theta for the x minus 5. And I'm going to use my right arrow key to get out of the absolute value. And then I'm going to do zoom 6. Okay. So that's what the absolute value of 9x minus 5 looks like as a function. Now, would this pass the vertical line test? Unfortunately, it would not, because if I draw a vertical line, and I'm going to do this, I'm going to go to y equal to, and I'm going to put, let's say y equal 5, and then press graph. You're going to see that graph of y equal 5 cross the absolute value function at 2 different places. So this would not be one-to-one. So that absolute value function does not have an inverse function, so it's not going to be one-to-one. Now, going back to this graph here, we're going to find out the intervals where it would have an inverse. Well, we know the problem would be at that point right here. Okay, because what's to the left of it, if we only consider what's to the left of it, we would have an inverse function. Or if we consider only what's on the right, that this part right here, only consider that part, it would have an inverse function. But if we consider the whole thing, we want to find out where is the problem point. And it's on the x-axis, so I know that the y value has to be equal to 0. So let's take that absolute value function, which is absolute value of 9x minus 5, and set that equal to 0 and solve for x. Now, normally with the absolute value equation, you'll write two equations. However, we're dealing with 0, and 0 is neither positive nor negative. We only write one equation, and that's 9x minus 5 equal 0. And then to solve for x, we're going to add 5 to both sides to get 9x is equal to 5. Divide both sides by 9. That means at x is equal to 5/9, that's where the absolute value, that's where the function would not have an inverse function. But if we take it piece by piece, to the left of 5/9, we would have just a plain inverse function. So from negative infinity to 5/9 would work. And then from 5/9 to infinity would work. Okay, so here, only this part here from negative infinity up to 5/9, this part would give us an inverse function. But then from 5/9 on, and we only consider this line, this part of the V-shaped graph, you would have an inverse function. Okay. All right, example 3. Now let's say we have a rational function, and we want to determine the intervals on which the following function has an inverse. Here we got f of x equals to 1 over x minus 6. F of x is equal to 1 over x minus 6. So here, let me take y equal to, clear both of these equations out. Let's see. 1 over x minus 6. In y1, I'll type in the number 1 divided by, put the x minus 6 in parentheses here. So I'm going to do left parentheses, get the x from xt theta n minus 6, close parentheses. And then I'm going to do zoom 6. Okay, and that's what the graph would look like. Now, if I was to apply the vertical line test, it would pass that vertical line test because I can draw a horizontal line down here. It's only going to cross the graph at one place. Or I can draw the horizontal line above the x-axis. It's still going to cross the graph at only one place. So if it has an inverse function, that means it is 1-to-1. Now we need the interval for this. Well, it's a rational function, so we need to find out what values of x that would give us a 0 in the denominator. So I'm going to set x minus 6 equal to 0 and solve for x. So that means x will have to be equal to 6. Okay. Now let's say they want the interval notation for that. Well, there's 6 over here. And in this case, at 6, we know we're going to have a 0 in the denominator. So we draw parentheses around the 6. Now, any x value less than 6 would work. And any x value greater than 6 would work. So the interval notation for our domain would be from left to right would be from negative infinity up to 6, and also from 6 to infinity. Those are the intervals where we would have a inverse for this particular function. Okay. All right, next we're going to talk about how to find the inverse of a function. Okay, we're going to find the inverse of a function. Now here is the directions or the procedure for finding the inverse of any function f. Number one, you're going to replace f of x with y in the equation f of x. It'll start off as f of x equal to something. So you'll replace f of x with a y, and then you'll interchange x and y. And then third, you're going to solve the equation for y. Now, if the equation does not define y as a function of x, then what that means here is that the function will not have an inverse function, and we end the procedure right there. Okay. Now, if this equation does define y as a function of x, then of course that function does have an inverse. And if it does, in step number 4, you're going to replace the y in step number 3 with f inverse of x. So here we can verify our result by showing this. F of f inverse of x is equal to x, and f inverse of f of x is equal to x. Here we won't be doing that for the sake of time, but we'll just apply that 4-step procedure for finding the inverse of any function. Like in example 4. Let's say I want to find the inverses of the following functions and restrict the domain of f if necessary. So here in part A, I get f of x is equal to 2x plus 6. F of x is equal to 2x plus 6. So following that 4-step procedure, I'm going to first replace the f of x notation with y. So the y is equal to 2x plus 6. Okay. All right, and then second, you're going to interchange x and y. That means the y becomes x, and that's equal to 2 times the x becomes y plus 6. So I get x is equal to 2y plus 6. And then we're going to solve this equation for y. Okay. So first we'll subtract 6 on both sides. That will give me x minus 6 is equal to 2y. And then to solve for y, we're multiplying by 2, so we'll divide both sides by 2. So that means y is equal to x minus 6 all over 2. And then replace that y, of course, with f inverse of x. So that means I have f inverse of x equaling to x minus 6 all divided by 2. That represents what f inverse of x is. Now let's look at part B. We got f of x is equal to x squared minus 1. F of x is equal to x squared minus 1. So here, I'm going to use that 4-step procedure by replacing f of x with y. So that means I'm going to have y is equal to x squared minus 1. And then I'm going to interchange x and y. So the y becomes x and the x becomes y. So the x is equal to y squared minus 1. And now I'm going to solve this equation for y. So I first add 1 on both sides. So it'll be x plus 1 is equal to y squared. Now, if you look at this equation right here, notice that the exponent for y is 2. It's 2 an even power. So that would tell me that this would not have a function. And in fact, it would not have an inverse function if it was just this. But we're going to restrict the domain. So let's go ahead and solve for y. The opposite of squaring something would be to take the square root on both sides. And notice that I'm including plus or minus because I'm taking the square root. So that means I'm going to have y is equal to, and it'll just be plus or minus the square root of x plus 1. Okay. Now, if I was to graph this on the calculator, I'm going to clear this out, go to y equal to, and I'm going to do second x squared for the square root, and then get the x for the x theta n plus 1. Let's say I wanted to graph this. Okay. This would only work if x is greater than 1. So from 1 to infinity, that would mean f inverse of x will be equal to the square root of x plus 1. Okay, now I'm going to enter the negative part in y2. That'd be negative, and then second x squared, and then get the x plus 1 and graph that. Okay. Now let's say we had this. We want to express the inverse of f of x is equal to 2x minus 1 in the form of y equal f inverse of x. Okay. So now let's start with f of x is equal to 2x minus 1. Let's start with that. We first start by replacing your f of x with y. So it'll be y is equal to 2x minus 1. Okay. And then interchange x and y. So the y will become x and the x becomes y. So the x is equal to 2y minus 1. And then we solve this equation for y. We add 1 to both sides, so there'll be x plus 1 on this side equals to 2y. And then to get y by itself, we divide both sides by 2. So that means y is equal to x plus 1 all over 2. And then replace the y with that f inverse of x notation. So f inverse of x will be x plus 1, the whole thing divided by 2. So that is the inverse of f of x equal to 2x minus 1. Okay. All right, for this one, here's another one. Let's say that f of x is equal to x minus 6, and that quantity is to the 5th power. And I want to find the inverse of that. Well, first replace your f of x with y. So it'll be y is equal to x minus 6 and that quantity to the 5th power. And then you're going to interchange x and y. So this y becomes x. That's equal to y minus 6 raised to the 5th. And then we solve this equation for y. Well, we need to get rid of the exponent of 5. We're raising y minus 6 to the 5th power. So the opposite of raising something to the 5th power would be to take the 5th root on both sides. And notice I do not need a plus or minus symbol because I'm taking the 5th root. I'm taking the odd root. If it was an even root, then I would need plus or minus. So the 5th root of y minus 6 raised to the 5th will be y minus 6, and that's equal to the 5th root of x. And then to solve for x, we're going to, solve for y, we add 6 on both sides. So I got on the left side, the 5th root of x, and then plus 6, that's going to be on the outside of the radical. It'll be equal to y. And then finally, replace the y with f inverse of x. So f inverse of x will be the 5th root of x plus 6. Okay. So that's how we find the inverse of a function. Okay, I'd like to return back to part B of finding the inverse of f of x equal to x squared minus 1. I only had like for the part for 0 to infinity, which was f inverse of x is equal to the square root of x plus 1. I also need to include the other part, the negative square root of x plus 1 for f inverse of x. And that's only for negative infinity up to 0. Okay, so only for 0 to infinity, it will be this f inverse of x. And then from negative infinity to 0, it will be this. F inverse of x will be equal to negative square root of x plus 1. So I just need to clarify that. Okay. Now, let's talk about how to graph inverse functions. Okay. The graph of a function and its inverse have a special relationship, which is illustrated in the following example. So here, we want to plot f and f inverse of x on the same coordinate axis. Okay. Now, what I can do here is take f of x is equal to 2x plus 6, which is part A, and create a table of values here. And I'm going to pick values like, let's say, -1, 0, 1, and 2. And in this case, we just substitute those values in for x to find out what f of x is. So if x is -1, this will be 2 times -1, which is -2, plus 6 will be 4. For x is 0, 2 times 0 is 0, plus 6 will be 6. For x is 1, 2 times 1 will be 2, plus 6, which will be 8. And then for x is equal to 2, 2 times 2, which will be 4, plus 6, which is 10. So here we can plot the points on the coordinate plane for f of x. So here we got -1 and up 4, and then 0, 6, then 1, 8, and then 2, 10. So if I connect those points, this will be the graph of f of x that's in green. I'll label this as f. Now, For the sake of it, let's do f inverse of x, or find out the equation for f inverse of x by letting f of x be y. So be y equals 2x plus 6. And then we interchange x and y. So this will be x equals 2y plus 6. And then to solve for x, we subtract 6 on both sides, which will mean x minus 6 is equal to 2y. And then divide both sides by 2. That would mean y is equal to x minus 6 all over 2. Finally, replace the y with f inverse of x. That would be x minus 6 over 2. That's what f inverse of x is. Now, to get the ordered pairs for the inverse function, if you look at your ordered pairs for f of x, all we have to do is interchange x and y. Interchange your x and your y coordinates. So for -1, 4, it will be 4, -1. And for 0, 6, if we interchange those ordered pairs, it will be 6, 0. 1, 8, interchange those ordered pairs, it'll be 8, 1. And finally, 2, 10, interchange that, it'll be 10, 2. And you can verify that by doing this. If x is 4, we substitute the x in our f inverse function with 4. 4 minus 6 will be -2. -2 divided by 2 will be -1. For x is 6, 6 minus 6 is 0, divided by 2 will be 0, and so on. Now let's plot those on the same coordinate grid. Let's see, 4, -1 will be to the right 4 and down 1. 6, 0 will be on the x-axis. 8, 1 will be to the right 8 and up 1. 10, 2 will be to the right 10 and up 2. Let's connect these points. And that would be the graph of f inverse of x. Okay. Now, what I'm going to do here is throw in the graph of the equation y is equal to x. That means if x is 1, y is 1, x is 2, y is 2, and so on. This blue line would be the graph of the equation y equals x, okay? Because the function itself and its inverse will be symmetric with respect to the graph of the line y is equal to x, okay? And that's always going to be the case for the function itself and its inverse. All right, let's look at part B. In part B, we got f of x equal to the square root of x minus 1. F of x equal to the square root of x minus 1. And I want to find the inverse of that function. Okay. Well, let's first find the domain, if at all possible. Here I'm going to take what's underneath that radical x minus 1, and I have to set it to be greater than or equal to 0. So if I have a square root function like this one, or a radical to an even power, even root, we have to set it to be greater than or equal to 0, because we can't take the square root in this case of a negative number, or any even root of a negative number. So to get x by itself, we add 1 to both sides. That means x is greater than or equal to 1. Okay. So if I create my table of values, I have to pick values of x that are greater than or equal to 1. Let's start with something like 1, 2, 5, and 10. And you're going to see why I chose those values here, because I chose those in a way so that when I take the square root of something, I'll get a whole number, like for x is equal to 1. If I do 1 minus 1, that's 0. The square root of 0 is 0. For x is 2. 2 minus 1 will be 1. The square root of 1 is 1. For 5, 5 minus 1 will be 4. The square root of 4 is 2. And then for 10, 10 minus 1 will be 9. And the square root of 9 is 3. So now you see why I chose those values for x. Okay, so now let's plot those on the coordinate plane. Do this in green. 1, 0 is on the x-axis. 2, 1 to the right 2 and up 1. For 5, 2 to the right 5 and up 2. And 10, 3 to the right 10 and up 3. This is usually what the graph looks like. It's like the square root of x, but it's just shifted to the right one place. And I'm going to go ahead and find the inverse of f of x equal to the square root of x minus 1. So here I'm going to replace f of x with y. So the y is equal to the square root of x minus 1. And then we interchange x and y. So this y becomes x, and the x becomes y. So the x is equal to the square root of y minus 1. And then we solve for y. Well, that y is underneath that square root, so the opposite of taking the square root would be to square both sides. That wipes out the radical. So that means I'll be left with y minus 1 on this side equaling to x squared. And then to solve for y, we add 1 to both sides. That would mean I will have x squared plus 1 is equal to y. And then finally, we replace that y with f inverse of x, which will be equal to x squared plus 1. Okay. Now here we're going to restrict it to values of x greater than or equal to 1. But notice with the inverse, if you have your ordered pairs, you can just interchange the ordered pairs. So 1, 0 will become 0, 1. 2, 1 will become 1, 2 if we interchange them. 5, 2 will become 2, 5. 10, 3 will become 3, 10. All right, now I'm going to graph this. Inverse 0, 1 would be on the y-axis. 1, 2 would be here. And then 2, 5 would be here, and 3, 10 would be up here. Connect those dots. That is what f inverse of x looks like. And the one in green is the graph of f of x. And if I draw in the graph of y is equal to x, Okay. I'm going to draw a dashed line for y equal x. Pretty much you can see there that these two are inverses because one, the graph of the function f of x is the reflection of the graph of f inverse of x. Right, let's look at one more of these inverse functions, graphing them and looking for the required symmetry. Here we got f of x is equal to 1 minus 6x. That's a linear function. So here, if I just draw or create a table of values, let's say 0, 1, negative 1. At x is equal to 0, that's 6 times 0 is 0. 1 minus 0 is 1. Then for x is 1, 6 times 1 will be 6. But here we got 1 minus 6, which will be negative 5. Then negative 1. A minus 6 times a negative 1 would be plus 6. So 1 plus 6 will be 7. Okay. Let's plot those on the coordinate plane. 0, 1 is here. 1, negative 5 will be to the right 1 and down 5. And then the other one, negative 1, 7 will be to the left 1 and up 7. So here's the graph of f of x equals to 1 minus 6x would look like. Okay. So that's the graph. Now let's look at f inverse of x. Okay, I'm going to find that by just letting f of x be equal to y. So it'll be y equal 1 minus 6x. And then you interchange x and y. So the y becomes x. It's equal to 1 minus 6y. And then next I'm going to solve this equation for y. Well, let's first subtract 1 on both sides. So the x minus 1 is equal to negative 6y. And then divide both sides by negative 6. This will be y is equal to x minus 1, all divided by negative 6. And then we substitute the y with the f inverse of x notation. So f inverse of x would be equal to x minus 1, all divided by negative 6. Okay, now for the ordered pairs for the f inverse, we just interchange the x and the y that we got here. For 0, 1, we just interchange those coordinates. So it'll be 1, 0. And then for 1, negative 5, interchange those, you'll get 5, negative 5, 1. And then for negative 1, 7, interchange those, you get 7, negative 1. All right, so let's plot those on the coordinate plane. Excuse me. 1, 0 will be here. Negative 5, 1 to the left, 5 and up 1 that's here. And then 7, negative 1 to the right, 7 down 1. Let's connect those and you'll have the graph of f inverse of x. So that's f inverse. And this right here in green is the function f. All right, so that's how we find the inverse of a function and graph the inverse of a function. All right, next we'll look at logarithmic functions. Now, for any base b greater than 0, where b is not equal to 1, the logarithmic function base b is denoted by y equal log to the base b of x. And that's the inverse of the exponential function, y equals b to the x, okay? So the inverse of the natural exponential function with base b equaling to e would be the natural logarithmic function denoted by y equals ln of x. So the natural exponential function, we have a base of e, like y equal e to the x. The inverse for that would be y equals ln of x. And of course, the y equal b raised to the x, it'd be log to the base b of x as its inverse. And also you need to know something else. Y equal ln of x is another way of saying log to the base e of x. On the next page, that inverse relationship between logarithmic and exponential functions may be stated concisely in several ways, like this. Y is equal to log to the base b of x, provided that b raised to the y is equal to x. Okay. So in other words, when we convert from logarithmic to exponential form, we start with the base. What's in front of the equal sign would be your exponent for your base, and then that's equal to whatever you're taking the log of. So y equal log to the base b of x means b to the y equals x. And then we have inverse relations for exponential and logarithmic functions. Here, if you have b raised to the log to the base b of x, that's equivalent to x. Okay, b raised to the log to the base b of x is equal to x, because b and log to the base b are inverses of each other. And also log to the base b of b to the x, since log to the base b and b itself are inverses, that's also equal to x for real values of x. And then the first one was for values of x that are positive, because of the fact that we can't take the log of a negative number, nor can we take the log of 0. And here's some logarithmic rules here that we need to be familiar with. The first one, if you have log to the base b of x times y, that's equal to log to the base b of x plus log to the base b of y. So here, log of the product is equal to the sum of their individual logarithms. We call that the product rule for logarithms. And then for the second one, log to the base b of x divided by y, you got the log of the quotient. That's going to be equivalent to the difference of the individual logarithms. Log to the base b of x minus log to the base b of y. We call that the quotient rule. And then the third one is the power rule, where you have log to the base b of x to some power z. That means we bring the exponent up front as the coefficient of log to the base b of x. So here, this is called the power rule or logarithms. You have log to the base b of x to some power z. That power goes in front of the logarithm as your coefficient. So it'll be z times log to the base b of x. And then the fourth one was log to the base b of itself will be equal to 1. Because you have to think of b to what power would give you b right back. And it must be the number 1. And these properties hold for natural logarithms as well. Okay. And here you see the graphs of y equal b to the x and y equal log to the base b of x. Those are inverses of each other. Here you can see that those two graphs are symmetric about the line y equal x. And then the second graph that you see here, log to the base b of x increases on the interval x greater than 0 when b is greater than 1. So that means the more you increase the base, then this shrinks in or gets towards the x-axis. And also notice something else, log to the base b of 1 is always going to be 0. So here the graph will be crossing the x-axis at the point 1, 0. Okay. All right, on the next page, here we got logarithmic functions with base b greater than 0 that satisfies the properties that parallel the properties of exponential functions given earlier. Here, the range of b to the x is going to be 0 to infinity. The domain of log to the base b of x will also be from 0 to infinity, because we can't take the log of 0 and we cannot take the log of a negative number. For b to the x, its domain is negative infinity to infinity, and that implies that the range of log to the base b of x is also negative infinity to infinity. And also b to the 0 is equal to 1. Because of that, it's going to follow that log to the base b of 1 has to be equal to 0. Because you have to think of this, b to what power is going to give you 1? And the only number that does that is 0. Any non-zero number to a 0 power is going to be equal to 1. And then if b is greater than 1, then log to the base b is an increasing function on x, of x. So if b is equal to e, then ln of x has to be greater than ln of y whenever x is greater than y. Okay. All right, in examples 9 and 10, we're going to solve some equations here. And these are logarithmic equations that we're going to solve. Starting with log to the base 4 of x is equal to 3, this example 9 in your handout. So if I want to solve this logarithmic equation, I need to convert that to its equivalent exponential form. That means I start with the base, which is the 4, which after the equal sign would be the exponent for 4. So this will be 4 to the 3rd. Then that's going to be equal to what I'm taking the log of, and that's the x. So that 4 to the 3rd is equal to x. Well, 4 to the 3rd is 4 times 4 times 4, and that's 64. So that means x equals 64 is what log to the base 4 of x is equal to 3 would be. And of course, you can check by just substituting the x with 64 by doing this. Log to the base 4, we replace the x with 64, must be equal to 3. Convert that to its equivalent exponential form. 4 to the third must equal to 64. And then 4 to the third is 4 times 4 times 4 is 64. So this checks. So 64 is the solution to that logarithmic equation. Okay. This next equation, example 10, here we're going to solve the equation for x. Log to the base x of 4 is equal to a half. Well, convert that to its equivalent exponential form. Your x is going to be the base. That 1/2 will be the exponent for x. So the x to the 1/2 equals 4. Now, another way of writing x to the 1/2 would be the square root of x. Okay. Square root of x is the same as x to the 1/2. So x to the 1/2 means the square root of x equals 4. And then to solve for x, we're taking the square root. The opposite of taking the square root would be to take the square on both sides of this equation. Square root of x, we square it, will be x. That's equal to 4 squared, or 4 times 4. That would be 16. So x equals 16 is the solution to this equation. And of course, we can do the check by doing log to the base x. We replace that with 16. 4 equals a half. And then 16 to the 1/2. If you convert it to exponential form, must be equal to 4. Well, 16 to the 1/2 is another way of saying the square root of 16, it should equal to 4. Take the square root of 16, it does equal to 4. So x equals 16 is the solution to that logarithmic equation. Okay, let's say we have this example. Assume log to the base b of x is equal to 0.87 and log to the base b of y is equal to 0.54. And here I want to evaluate the expression log to the base b of x divided by y. In this case here, I'm doing the log of the quotient, and I'm going to apply the quotient rule that I just got through talking about. Anytime you have a log of a quotient, you write that as the difference of the individual logarithm. So it'd be log to the base b of the numerator, which is x, minus log to the base b of the denominator, which is y. And then we can substitute those values here. Log to the base b of x is 0.87 minus log to the base b of y, that's 0.54. And then we subtract 0.54 from 0.87, you'll end up with 0.33. So log to the base b of x divided by y would be 0.33 based on these values that are given to me. All right, example 12, let's say log to the base b of x is 0.45 and log to the base b of z is 0.84. And I want to evaluate the following expression, log to the base b of x times z. Well, in this case, I have a log of the product, x times z, that represents a product. So I have a log of the product. I can write that as the sum of their individual logarithms. So it'll be log to the base b of x times log to the base b of z. And then we substitute. Log to the base b of x is 0.45 plus log to the base b of z was 0.84. And then 0.45 plus 0.84 would end up being 1.29. So log to the base b of x times z ends up being 1.29 based on this given information. Okay, example 13. Let's say we got log to the base b of the square root of x divided by the cube root of z. Well, notice right off the top, I have a numerator and a denominator. That tells me I have a log of the quotient. I need to apply the quotient rule by expanding this as the difference of the individual logarithms. So here, this will be log to the base b of the numerator, that's the square root of x, minus log to the base b of the denominator, that's the cube root of z. Now, I'm going to write these radicals in its equivalent exponential form, like the square root of x. So let me bring down log to the base b of square root of x. If I write that in its equivalent exponential form, it will be x to the 1 over 2. The 1 comes from the exponent of x. The 2 is that understood index in the square root. So square root of x will be x to the 1/2. Then minus log to the base b of z. The exponent for the z is the understood 1 over this index for this radical 3. So the cube root of z will be z to the 1/3 power. So I have log to the base b of x to the 1/2 minus log to the base b of z to the 1/3. Now, on each one of these terms, I can apply the power rule by bringing each power in front of the logarithm. So for log to the base b of x to the 1/2, I'll pull the 1/2 in front. That would be my coefficient for log to the base b of x minus log to the base b of z to the 1/3. That 1/3 is my exponent. I'll bring that in front of log to the base b of z. So on each one of those, I had to apply the power rule. Now let's do some substitution here. Log to the base b of x is 0.38. So I'm going to have 1/2 times 0.38 minus 1/3 times log to the base b of z is 0.83. Now, if I simplify this, I'm going to do 1 divided by 2, and then times 0.38, close parentheses, minus 1 divided by 3, and then in parentheses, 0.83. Let's say I want to round this up to 2 decimal places. Let's see. 0.8 is the second digit after the decimal point. To the right of it, it's a 6 is greater than 5, so the 8 increases to a 9. So this will be negative 0.09. So log to the base b of the square root of x divided by the cube root of z would end up being negative 0.09 based on this information that's given to me. Okay. And on the next page, without using a calculator, solve the following equation. 4 to the x is equal to 26. In this case here, this is one of those exponential equations that we solved in college algebra. Okay. So here the base is not going to be 10, so that means we have to take the natural log on both sides of this equation. Okay. You start by taking the natural log on both sides. You want to have the exponential part by itself, and then take the natural log on both sides. And now we're going to apply the power rule on the left side by bringing the x in front of the natural log of 4. So the x times ln of 4 is equal to ln of 26. And then to solve for x, it's being multiplied by ln of 4. So we divide both sides by ln of 4. And this will be x is equal to ln of 26 divided by ln of 4. And I will go no further than this. So in other words, they were looking for the exact value. So the x is equal to ln of 26 divided by ln of 4. Finally, we'll look at the change of base property, also taught in college algebra as well. For the change of base rules is this: we're going to let b be a positive real number where b is not equal to 1. Then b to the x is equal to e times ln of b to the x is equal to e raised to the x times ln of b for all x, and log to the base b of x will be ln of x divided by ln of b, where x is greater than 0. And more generally, if c is a positive real number, whereas c is not equal to 1, then b to the x is equal to e to the x times log to the base e of b for all x, and log to the base b of x will be equal to log to the base e of x divided by log to the base, well, actually c, that should be c, log to the base c of x divided by log to the base c of b. Okay. But we're just going to focus on these last two right here. Okay. And that's just going to be log of x divided by log of b. And also we can use ln as well, which is this right here, ln of x divided by ln of b. Okay. So in this case here, in this example, let's use our calculator to find the value of the logarithm rounded to 4 decimal places. Using that change of base rule, log to the base 4, 22. Now you can use common logarithms or you can use natural logarithms. Okay. But here, I'm going to go and use natural logarithms. I'm going to write this as ln of what I'm taking the log of, which is 22, divided by ln of whatever my base is. That's 4. Now to enter this in the calculator, we're going to do this. Press the ln key on the left-hand side, then type in 22. Make sure you close the parentheses around the 22 because you only want the natural logarithm of 22. And whatever that is going to be divided by ln, press the ln key on the left side, and then 4, close parentheses, then hit enter. Now the 4 decimal places, this will be 22.97, and the 7 remains the same. So it'll be 2.2297. Now, had you use common logarithms, you'll get the same answer. This will be the log of what we're taking the log of, 22, divided by the log of my base, which is 4. And these are common logarithms, by the way, because they don't have a base here. It's understood to be log to the base 10. So in this case here, press the log key and then 22, close parentheses, divided by log key again, and then 4, close parentheses. The same answer, 22.2297. All right. Okay, on the next page, also using the change of base rules here. Say we got log to the base 3 of 53. Log to the base 3 of 53. I'll go ahead and write this out. Okay, Now you can use common logarithms or natural logarithms. It doesn't matter. I'm going to use natural logarithms here. So this would be ln of what I'm taking the log of, that'd be 53, over ln of 3. And by the way, it does tell us to use natural logarithms anyway in the directions. It says write the following logarithm in terms of the natural logarithm. All right, so now using the calculator, it's going to be ln 53, close parentheses, divided by ln 3, close parentheses, and then enter. So the 4 decimal places, there'll be 3.6139, and the 1 will keep the 9 as is. So it'll be 3.6139. For log to the base 3 of 53. And finally, convert the following expression to the indicated base. Here we got log to the base 5 of x squared plus 6. Log to the base 5 of the quantity x squared plus 6. Now here we're going to be using base e. And what that means is this. Log to the base e of x, that's another way of saying ln of x. Okay. Log to the base e of x means ln of x. So that means for log to the base 5 of x squared plus 6, I'm going to do ln of this expression here, x squared plus 6, divided by ln of the base, which is 5. And of course, I will go no further than that. Okay, and I cannot take it any further than that. So the final answer for log to the base 5 of the quantity x squared plus 6 will be ln of the quantity x squared plus 6 divided by ln of 5. Okay, so that does conclude this video on section 1.3 dealing with inverse, exponential, and logarithmic functions. Please feel free to email me if you have any questions about anything that's presented in this video or any other homework that's in my math lab on this section 1.3.